So we've moved into clearly into the quantum mechanical realm of the atom. We've moved from the billiard ball model to the solar system model, and then we're noticing that that maybe atoms aren't made up of particles. You've probably watched the video about de Broglie, who apparently was fairly eccentric, and came up with this concept: what if we just treat everything like a wave? And although it was well outside of everybody's experience, it sort of met with everybody's understanding. Okay, now we'll see if this works. I'm just going to share my screen for just a second, and we're going to look at what is the different models of the atom. Okay, so we start out with our billiard ball model. Now this crashes every once in a while, but we can just start it up again. So here comes our light. That's a billiard ball. Can you see what's happening there? As the photons come in, they're just going to bounce off it. And that is not what we were seeing. We were seeing a spectrum of things. Okay, let's go to, here is the plum pudding model. And so here's J.J. Thomson. And what he's saying is there's a large area of positive charge. And as the photons come in, they interact with the electrons. The electrons can absorb and release them. Okay, so classical solar system model. Let's see how this interacts with the light. So there it is, and it explodes before anything can happen because the positive and negative charges are so powerful, and an electron should, in fact, radiate away all of its kinetic energy as electromagnetic radiation. That is impossible. So along comes Bohr, who in fact doesn't care at all about whether an electron is a particle or something else. In fact, Bohr was pretty clear. You don't have to have any idea of what the particle actually looks like. And so you see an electron. There, the electron's absorbed a photon of a specific wavelength, and it has jumped up an energy level. And we'll see in just a second, that electron will radiate its photon in some direction. And will it absorb? No. And so in this case, it's only interacting with our ultraviolet. There we go. Now the electron's jumped up to the 6th energy level. It's way over here. Okay, and now we'll see. Does it fall back down? So there, it's emitted that ultraviolet photon again, and it's jumped back down to n equals 1, the 1st energy level. Okay, here comes de Broglie. And so there's the wave mechanical model. So now, if you can see, so you can see the electron bobbing away there. The electron in this model is no longer a single particle. Now the electron's actually just a wave. And for that wave to exist, to be able to resonate, it has to reach a certain position so that it resonates rather than vibrates destructively. Okay, and those result in the discrete energy levels. So this was the experimental evidence that de Broglie was able to explain very clearly with the quantum mechanical model. The electrons are going to fit into specific energy levels if they are waves with a specific wavelength. And so they can absorb energy. The wave can become longer and we'll get more wavelengths, but it has to be at a resonant level. It has to be at an energy level that allows the electron to resonate. Now, we also had a look at the Heisenberg uncertainty principle. And Heisenberg basically said you can't tell the position and the momentum of an electron at the same time. You can tell one, but not the other. And it didn't matter which one. And so he came up with the Schrödinger wave equation, which just says you can only describe electrons as probability clouds. And so this is actually like a wave probability model. And so now, instead of these discrete waves, now there's a probability cloud. And a probability cloud just tells you what the probability, A probability cloud basically is densest where the highest probability of finding the electron is. Okay, so this is a hydrogen atom in its ground state. So let's turn it on and let's see. Okay, so notice here, it's absorbed a photon. So this is now the electron probability cloud when it's excited in the third shell. So notice the cloud has dispersed. It's in a very specific shape. And if we just run it ahead, the electron is going to release a photon. So there it goes. It's fallen back down to the first energy level. And that's what the probability cloud looks like on the first energy level. It's just kind of spherical. Okay, let's see if we can make this work in a video conference. So this gives us an idea why, at least I hope it gives us an idea why. Maybe it doesn't give us any idea, not sure. So this gives us an idea why electrons can only identify particular positions around the nucleus where they resonate. And this is in keeping with de Broglie's model. So this is a little wire, and we're actually going to vibrate this wire. So there's going to be a wave that travels around this wire. In other words, a wave traveling in a medium. And you'll see that we can build up a wave only at very specific frequencies, the same way we can only have electrons occupy very specific energy levels. Okay, so hopefully this works, and hopefully it shows up. And is it on? I don't think it's on. Well, that's a wash. Okay. Boo. Oh, here we go. Helps if you have... all right. Oh, look at that. It's at 30. Put something white behind it. And does it help at all? Doesn't help at all. The white actually makes it worse. Okay. Yeah, it is. Okay. All right. Oh, what about a physics textbook? Would that work? Wait a minute. What about this? Does it help at all? Okay. Yeah, it's not terrible, but it's not great. So you can actually see that we've got a kind of a wave going on here at 30 hertz. Okay, what I'm going to do, I'm going to bump up the frequency. Oh, there we go. It's quite a bit more dramatic. Okay. So now you can see that we generate a standing wave in this loop. So we can have a standing wave at about 31. Does it get any better? Oh, look at that. Okay. Here we go. So we can get a standing wave somewhere around 33, 34. But if we increase the frequency, suddenly we can't get a standing wave. There's no resonance. The energy is actually the energy is actually destroying the standing wave. Okay. But we might be able to find yet a second frequency here, and we're going to see another standing wave. Okay, so we're putting more energy in. It's still destructive at 60. Not getting any resonance, not getting any resonance. So let's go up. Let's go up to, I don't know, about 120 maybe. Just get, oh, there we go. Okay. So as you can see, we've got a second set of standing waves, okay? So just like the electron can only occupy certain energy levels, it has to exist as a wave, and so it can't occupy energy levels in between. Otherwise, the waves destroy themselves, okay? So that was 60. Once again, no resonance here. Let's keep bumping it up, and let's look for 240. In other words, just about twice. Where am I? See if we can find another one. Oh, I think I hear one coming. 260? No. Okay, we're not going to find it. Oh, there it is. Okay. Tweak it a bit. Nope. Okay. Anyways, you get the idea. Electrons can only exist in energy levels where they resonate properly. They can't exist in between, and so this explains that quantum nature of the electron and the quantum mechanical structure of the atom.